Joaquin.
Thank you for having me. It's been a pleasure visiting. I'm going to talk about the Terahertz Intensity Mapper. I'm going to start with science motivation, talk about the history of cosmic star formation and line intensity mapping. I'll introduce the TIM instrument and then talk about the specific science TIM will do. And then kind of at the end pontificate a little bit about where line intensity mapping is heading. So the idea of line intensity mapping is kind of new. People have been trying to do these things. If you're familiar with 21 centimeter in the radio, that's line intensity mapping. People have been thinking about this. If you're a physicist, you think of this as astronomy. If you're an astronomer, you could think there's no sources actually detected, so it's kind of like physics. It's kind of like in this in-between space. I often think about it in terms of like a CMB experiment where with the CMB, we're used to seeing this two-dimensional structure, and how we actually analyze it is to make a map and we Fourier transform that and measure the power versus physical scale. Line intensity mapping is very much like that, but in redshift slices. So we'll map with an integral field unit spectrometer, make a 3D map of the universe, break that up into slices, and then analyze each slice independently, then bin that up and understand how the universe evolves over time, kind of at intermediate redshifts between today and the beginning. There are some review articles that I'll point to along the way. But the idea is that line intensity mapping is going to survey the 3D structure of a massive cosmic volume. And this is kind of a regime that has not been probed before. So this LIM is a unique technique that's kind of emerging. And the idea is to efficiently measure the aggregate spectral line power from galaxies, not bothering to try to detect individual galaxies, but the aggregate diffuse emission from all those galaxies, and build up this 3D map of cosmic structures. So we're not attempting to individually detect a single source. And this will grant unique access to signatures of fundamental physics, which would connect the smallest and the largest scales, and measure kind of things like the cosmic star formation rate, gas mass density, and so forth. Eventually, we could use this as a cosmological probe, but we're probably another 20 years from there. These are from a review and a COMAP, but this shows a simulation of all the galaxies in the simulation. Red indicates what would be detected in like an optical galaxy survey with selects on stellar mass. And this shows the kind of blurred out image of what you would see if you were seeing in CO or C+. Okay, so just a fuzzy kind of confusion limited blob. This is a simulation done by COMAP, which shows, again, in stepping through redshift slices, all the different galaxies in the catalog, and then what you would see from, in this case, CO. So that gives you kind of a general idea of what we're trying to detect and measure. Just to get everybody on the same page of what wavelengths we're talking about, this is the electromagnetic spectrum as it gets through the Earth's atmosphere. I'm talking about the far infrared, which is typically defined as 300 to 200. Here I'm actually, I'll be referring to kind of far infrared as sort of 200-ish to 500-ish, but in this range right here, the key point is that the atmosphere is completely 100% opaque. So to see any astrophysical sources at this wavelength range, we have to get above the atmosphere into space or onto a suborbital platform like a balloon. So that's what I'm talking about. First, I'm going to start here, and this is just the spectrum of the cosmic background. So if you ask what is the color of the sky, this is the color. And you see the brightest thing on the sky is the cosmic microwave background, the radiation left over from the Big Bang. That is the brightest thing. The next brightest thing on the sky should be the aggregate light from the history of cosmic star formation. So all the stars over all of cosmic time produce UV photons, and the sum of that over cosmic time should be the cosmic optical background. When people set out to measure this, they kind of instantly realize that there's something even brighter called the cosmic infrared background. And what that is that there's dust always surrounding star formation, and so half of the energy produced since the Big Bang has been absorbed by dust and re-emitted here in the infrared. So most of the photons were originally emitted here, they're absorbed by dust, and they actually come out here. So to understand the half of the history of the universe since the Big Bang, we have to investigate the infrared background because the optical is only half that story. Other things on here, X-ray background, you can kind of think of this as the history of black hole accretion. Also radio, which is a combination of star formation and background, and AGN. Okay, cosmic dust. So I started life as a CMB instrumentalist. dust was merely an annoyance. In the part of my thesis, in progress of my thesis, I started kind of learning about dust, and now I'm like a big dust fan. Like I think dust is fascinating. So dust was first noticed about a century ago by astronomers attempting to understand the structure of the Milky Way. Basically, they were noticing there were fewer stars in some directions, which they quickly realized were not because there were fewer stars, but because there was something absorbing the light. the IRAS satellite kind of did the first systematic study of dust across the sky in 1983. And then shortly after, COBE satellite made that measurement that showed that half of the energy produced since the Big Bang has been absorbed and re-emitted by dust. So IRAS showed that there's basically invisible objects all across the sky on large scales and small scales. There's galaxies that are invisible in the infrared, and there's structures at even smaller scales, like around stars, that were otherwise invisible. So some of the kind of considered greatest hits of IRAS were the discovery of infrared galaxies, and also the discovery of protoplanetary disks and debris disks around nearby stars. Where does this dust come from? Most of this is produced by stars at their end of their life. So in the current epoch, nearby us in redshift, that's mostly produced by AGB stars, asymptotic giant branch stars at the end of their life that basically start pulsating and shedding dust. In the early universe, there hasn't been time for these massive stars to evolve, and so it's supernova remnants. So basically in the early universe above redshift 6, most of the dust should have been produced by supernova. In the local universe, kind of below redshift 6, it should have been produced by AGB stars. It's dominated by AGB stars. Key point is that star formation always occurs behind a veil of dust. So if you want to see how structures form, how stars form, you always need to look at the dust or through the dust. And dust is a crucial constituent of the formation of everything from planets up to supermassive black holes. It also represents the rise of complex chemistry in the early universe, and some think it can be a catalyst for the ingredients necessary for life. You can think of dust, like what the grains actually look like, are kind of like exhaust from a car or exhaust from a barbecue, but that's kind of the carbonaceous grains that we think of. If you take a galaxy, which is made up of stars, and you sum up all the starlight, this is what that spectrum would look like of a galaxy. This is without dust. This is the blue. You see that it's dominated kind of in the UV. Bulk emission kind of peaks around 1 micron. If you then add in dust to a galaxy, that spectrum is processed by the dust. Most of the UV light is absorbed. The dust grains heat up, and it re-emits here in the infrared, peaking around 100 microns or about 30 Kelvin in terms of temperature. Okay? So this is what an actual galaxy looks like. This is the unprocessed starlight. Okay? You can break apart that cosmic infrared background and the optical background into the cosmic star formation history. This is a fundamental plot in cosmology that shows the construction of all structure in the universe over cosmic time. What we see here in terms of star formation rate, or its integral, the integrated stellar mass density, you see that over time, more gas is converted into stars, and so the total amount of mass in stars increases. The derivative of that is the cosmic star formation rate. What we see is that there's an increase from earlier times to a peak about redshift 2, and then a slow decline. What's happening is gravity is collapsing building structures. The free dispersed gas is being converted into stars. At some point, that star formation process turns off or is quenched, and we go down to the current epoch, where there's about a 2 orders of magnitude difference in terms of the co-moving star formation density. I showed the wrong one. I thought I skipped that one. This is a really cool plot done locally that just shows the kind of current status of things. So this is very old. This has been corrected for dust here, but this kind of shows the actual problem. So if you just take the UV light and ask its star formation rate, this is the answer you get. You have to assume a dust absorption and then correct for that. If you look in the infrared, there's a much smaller correction. You're kind of seeing the bulk of what is actually forming stars. So black is the total star formation rate, which is more proportional to infrared. This is the dust obscured. This is the unobscured. you see that there's huge kind of uncertainties at high redshift. As you go to higher redshift, those uncertainties become even greater. And the fraction of obscured star formation is changing over cosmic time, but it also changes by source type. So at high redshift, the most massive galaxies are very dust obscured, and some of the lower mass galaxies, which are contributing to the bulk of star formation rate, can be less obscured, but the most massive ones are heavily obscured. This is just a cartoon of kind of what's happening in a galaxy. Basically, you have a turbulent reservoir of gas, cold streams and tidal streams that can be driven by mergers or just small satellites being absorbed, kind of come together, make shocks, bursts of star formations happen. This is a simulation from Chris Hayward of one of the more intensely forming star formations of galaxies of what they look like. At the most massive end, they tend to be driven by major mergers. At the lower mass end, they can be driven by small mergers from satellites. But turbulence and shock is what's kind of making these clouds collapse and form stars. This is a local analog of a star-forming galaxy. This is ARP 220 taken with Hubble, but you see the correspondence here in terms of the optical, where you can see the dust, you see the disturbed morphology. This is where the bulk of star formation is kind of happening in the most intense regions. JWST is pushing our view of this out to higher redshifts. We're now seeing things out to redshift 14, but you see it's just kind of a handful of sources. And so this is a compilation of kind of most recent constraints on the star formation history going out to redshift 8. By the time JWST and Euclid are done, we will have a better view of this, but remember those are still merely tracing the unobscured light, and we still need to kind of measure the obscured star formation to get that full picture. I showed you the spectrum of the universe, but this is the spectrum of the universe in individual lines. So these are the brightest lines on the sky. One of the brightest lines should be Lyman alpha. It's heavily affected by dust, scattered, so it's really difficult to trace a Lyman alpha photon basically from its source, either because it's absorbed or scattered by dust or gas in between. The brightest line then available is actually the ionized carbon at 158 microns, shown here. And just for reference, this is from a really nice paper by Riley Hill and Douglas Scott from 2018, where they put all this together. There's CO lines, molecular CO lines here. You see there's a forest of lines. This is the sum of all of them. The point, and these are the other far infrared lines like O, 1, 2, and 3. The point of this here is that if you're going to use a single line, or if you ask what is the brightest line on the sky, it's ionized carbon. Okay? And so if you want to try to map out structure of a single line, it's ionized carbon you want to aim for. So far infrared and millimeter lines, these are the most direct dust insensitive probes of the cold interstellar medium and its energetics across cosmic time. The lines are the dominant cooling channels of gas. They're optically thin, so they trace the entire galaxy, unlike most optical lines, which are only tracing kind of the shell or the outskirts or the suburbs of a galaxy. These lines can trace the star formation rate, star formation potential, density, ionization, metallicity, and kinematics. Historically, the atmosphere has blocked the transmission of these lines, and so we've either had to go to space or just get above the atmosphere. There's also kind of technical barriers to measuring these lines, because it's not like the optical where one photon can kind of bang into one electron and detect an electron, and they're too high frequency to detect directly like in the radio or coherently. So there have been technical barriers and logistical barriers such as the atmosphere and detector technology that's made this very difficult. But in terms of the brightest lines here, you see again C+. Other bright lines are like O3 88 microns, O1 63 microns. I'm going to refer to this spectrum from ISO of M82. There's M82 just for reference, but most of these lines are from M82. Oh, and here you see there's the CO ladder. Every 115 gigahertz, you get a rotational transition. Okay, so the specific line ionized carbon, or at 158 microns, sometimes called C+, this is one of the major coolants in the ISM. It can be 0.1% of the entire luminosity coming out in one line. So the entire emission of this galaxy, 0.1% can be coming out in that one line. It's a mostly extinction-free probe of the physical conditions of the gas and radiation fields. ALMA has opened up these observations at high redshift, like basically redshift greater than 4. But below that, you need to get above the atmosphere to observe this. And this is, can be used as a tracer of large-scale structure in the cosmic star formation history. This shows the observed wavelength band of TIM and the various lines that are possible to observe. This shows the mean line brightness of the various lines. This is C+. So even though there are many lines at many redshifts, C+ is so bright that we have about an order of magnitude contrast between the kind of next brightest lines. So one problem of observing in CO is that you can have interloper lines that gets a little bit confusing as to which line you're actually seeing at each redshift. We would be lucky to have that problem with C+, because it's going to take a decade for that to be a problem for us just because of the signal noise. But so for now, we can kind of just shove that under the rug and ignore it, which is nice. So the lines that TIM can see, so TIM is going to observe from 240 to 420 microns, which is 700 to 1200 gigahertz. That will get TIM C+ redshifts, just for reference, between about 0.5 and 1.5. It can also, in principle, detect 88 microns and 63 micron oxygen lines at higher redshifts, but those are going to be very difficult. Why do you need to get above the atmosphere? Basically, getting above the atmosphere buys you about a factor of 100 in mapping speed, just because of the transmission of the atmosphere. Also, you get the entire bandwidth that you can observe at. So even if you just picked kind of a small atmospheric window that you could look at from the ground, you can, an hour from a balloon is about 100 times more sensitive than from the ground. So if we can get 200 hours from a balloon flight, that would be spending something like 20,000 hours observing from the ground. So that's why you go from a balloon. There's many reasons not to want to go to a balloon, which I can also talk about, but that's the reason why you want to go there. And also, in addition to just total mapping speed, it's also really nice not to have to deal with atmospheric fluctuations and more bandwidth that you can observe at. So those are all good things. So this is the observability of C+ versus redshift. So this shows the main windows from the ground. There are smaller windows here, but you see you don't have kind of access to a large redshift range. There's a big window from redshift 5 to 8 that ALMA can observe at. Also redshift greater than 10 in principle, you could be observing this, which ALMA has been successful at seeing. But from a balloon, you can basically access kind of the entire redshift range of C+. This is the kind of landscape of line intensity mapping experiments that you'll see. These are lower frequency coherent detectors targeting CO, it's like COMAP. These are typically millimeter wavelength intensity mapping experiments with spectrometer on a chip bolometers, kind of similar to CMB type experiments. These are two balloon experiments. Exclaim was not selected for the second round of funding, but TIM is going. And this just shows where it is. So TIM is the highest frequency. In terms of C+, that means that we're tracing the peak of cosmic star formation history. In terms of redshift or physical scale, these are all the various experiments that are doing intensity mapping. Here you see TIM is down here, so it's a relatively smallish field at relatively lowest redshift. I'll talk about why we're choosing to do that. And then this shows the modes on the sky in terms of parallel or perpendicular lines that we'll be sensitive to. This is all in this review from here. Okay, this is kind of current limb constraints on, in this case, cosmic gas density. And this is from, Cardo Keating made this, who's a close collaborator of HIA through SMA. But these are kind of observations through, with ALMA and CARMA, amongst others, showing models and solid lines. You see that there's basically an order of magnitude discrepancy across all redshifts in terms of what this is. This is a fundamental measurement of structure formation and cosmology that's just beginning to be constrained. And this is the type of measurement that line intensity mapping is going to be really good at over the next decade. So the idea for TIM kind of came as a merger of kind of two different platforms. One was the spectrometer, which started life as Z-Spec, which was on the CSO. Then we moved down to apex, and so there was a team, and we were thinking about kind of what to do with this technology after a single pixel spectrometer on apex. Then there was the BLAST TNG design, or BLAST design, which was basically Herschel's spire on a balloon. And they were doing continuum, then when they had done continuum and extragalactic stuff, they switched to polarization. And then it was, what do you do after that? And the idea was to turn this into a spectrometer with this technology. At the same time, around the time of the decadal, we were studying a design for what was originally called Far Infrared Surveyor, then became Origin Space Telescope, then in the decadal was proposed as SMOKE, and then when an actual call came out, it was for a Far Infrared Probe, which was eventually selected for a Phase A study by NASA about a year ago that was called PRIMA. So it was this kind of landscape that we were thinking about to do some sort of intensity mapping in the far infrared on a balloon platform as technology development for this, but also to get a spectrometer into space and start doing intensity mapping. So this is TIM. This is a funded balloon-borne NASA mission. It's about, depending on how you count, about a $15 million project. There's a 2-meter primary mirror, which I'll talk about each of these components in a minute. This integral field unit spectrometer operating from 240 to 420 microns. It's about 7,000 detectors in 2 spectral channels and about 50 spatial channels. So basically it's a long slit split into 2 bands, and we scan it across the sky like this. So each spatial pixel gets dispersed, and so we build up our spectrum by scanning. We'll measure C+ from redshift 0.5 to 1.6. We are scheduled to launch basically exactly a year from now. We'll be heading down to Antarctica. This is the team, the major components. So the project's led by University of Illinois, which does overall project management, also the camera. Arizona State University, led by Chris Grappi, does the cold optics and detector readout. JPL with Matt Bradford and Rainier Jansen does the detectors. Penn, led by James Aguirre, is in charge of the gondole and flight software. And University of Arizona, led by Dan Maroney and Ian Lowe, are in charge of the primary mirror, the overall optical design, and the engineering and the systems integration. So basically the high bay is there, so that's where we put everything together. I want to call out 3 of our junior scientists that have taken on major roles in the project. So Rainier Jansen is staff scientist at JPL. He's in charge of the detectors. Ian Lowe is a postdoc at University of Arizona. He's the TIM instrument scientist. And Jessica Zabrowski is a NASA Hubble Fellow about to transition to faculty at UChicago, and she's the analysis lead. This is an actual simulation of the volume TIM will observe and the fluctuations that we'll see and the blind detections we may hope to detect, like individual detections of galaxies shown in black. So the main science goals are to spectroscopically measure the cosmic star formation via line intensity mapping with the C+ lines. That would be the first. This shows the cosmic star formation rate. Same plot basically I'm showing. This is just an old version I had. Model shown in dashed line. Again, you see there's huge discrepancy. This is the unobscured UV light and uncertainties. There's the infrared light. TIM will be measuring in this band right here. So at the peak of cosmic star formation rate. We will also perform a stacking analysis and cross-correlation analysis to study the C+ emission of galaxies. This has not been done. We have looked at kind of individually relatively bright galaxies with ALMA and so forth, but we don't know what the average C+ luminosity is across redshift. And that's a huge uncertainty in what we're going to see and what our signal is and for forecasting. So that's the kind of guaranteed science is actually this, and that will be an important feedback to forecasting next generation's intensity mapping experiments. We've also been looking at, there's only so much time we can observe our main deep field. So we've been investigating doing pointed spectroscopic observations of lens galaxies to measure O1 and O3. This is science that is just out of reach of ALMA, and there's not currently a space-based platform to do far infrared astronomy, so this is unique phase space for us. And we've been looking into doing galactic observations. So if you're interested in any of these, I'm here for the rest of the week, come talk to me, I'd love to talk to you. Okay, here's the actual design. This is the optical design. Here's the 2-meter primary mirror. It feeds a 0.5-meter secondary, then goes into the cryostat shown here. the cold optics and grating spectrometer are in here. The detector focal plane is about there. This is the primary mirror. 2-meter mirror. There's a carbon fiber backup structure with machined aluminum panels basically bolted onto that with adjusters. This looks really similar to ALMA and SBT, also CCAP prime, and so forth. This is kind of a standard design. The spec was, the requirement was to get this surface better to 10 microns. We measured it at 6 microns, so this has been great. Just for scale, this structure cost about $1 million, which is why we didn't test fly it. So I'll talk about that in a bit. But this was one of the, when we started the project, this was the thing I was worried about most, was the mirror and how to afford it. In the end, this thing came in under budget and ahead of schedule, and it was like the only thing on the project that did that. So this was a great success. The cold optics were designed and fabricated by Arizona State University, led by Chris Groppe. This is the this is the CAD drawing of it, just showing, so light comes into here, gets split into 2 bands, a long wavelength and a short wavelength, and then everything's independent from there in terms of grating and focal plane array, but it's more or less a mirror just scaled by wavelength. A mirror image. So this is a monolithic optics package, everything's bolted together, and it's all enclosed by a 4K radiation shield. Like I said, it's 2 distinct long slit gratings. So on the sky, this will be 1 long slit at each at 2 different wavelengths. Each spatial pixel then disperses the light into the 2 bands. This is the cold optics mounted to the cryostat in the Illinois lab a few months ago with the team. The cryostat, this started strong heritage from the BLAST design. It was fabricated at Meyer Tool in Chicago. Compared to BLAST, we had to accommodate more complicated optics, so the diameter had to get larger. This pushed us over a threshold for fabrication, which made it more expensive and difficult to build. We also had to have a larger volume of helium for the hold time. But this is a single cryostat. It's just liquid helium with 2 nested vapor-cooled shields. Inside is custom 3-stage kind of helium-10 sorption fridge made by Chase Cryogenics. The cold stage gets to 250 millikelvin. That's where we need our temperature, our stage temperature to have for the kids to have photon noise limited performance. The full weight of this thing is about 500 kilograms, and it will have a hold time at flight of about 20 days. Just for scale, there's a graduate student with the full cryostat. You could fit probably 3 people inside there. So it's very big. We had to actually to build this at Illinois, we had to cut a hole in the roof and build a 2nd story of a roof just to fit that in. The detectors, these are aluminum kinetic inductance detectors. It's nice because the fabrication compared to a transition edge sensor is very simple. It's a single layer, and it basically works kind of like as an FM radio station, and you tune the frequency of the LC circuit by the capacitor. The inductors are all the same. So there are 2 times 3,600 horn-coupled aluminum connected inductance devices. So this shows one of our focal plane units. I forget if this is long wavelength or short wavelength, but basically there's 4 wafers that make up the focal plane, and there's 2 of these. We've demonstrated and actually exceeded our sensitivity requirements. All of these will be read out by Xilinx RF SOC readouts. So we'll have 2 of these that read out about 1,000 each. 2 of these RF SOC boards, each has 4 channels. Each reads out about 1,000 detectors. So we need 1 board for each array. These are the detector specifications. So these are photon noise limited. Detector time constant is about 40 microseconds. The 1/f is somewhere less than 1 hertz. We'll know for sure when we're at float, but it'll probably be about 0.1 hertz. The RF SOC has been demonstrated does not add significant noise. The actual horns are fabricated at University of Virginia by Brad Johnson's groups with Peter Dow. So this is the CAD drawing just showing everything, including basically the spacecraft. So the balloon is way up there. I'll show you that in a bit. But here, there's all things hanging off it, like sun sensors to know where we're pointing, solar panels to give it power, telemetry antenna to transmit. We have a sun shield going around everything. This is a static big sun shield that goes around everything. And then there's also a co-moving baffle that moves with the mirror. This is the elevation axis, so the whole thing moves up and down about this. And then it rotates from the pivot up there using a reaction wheel, which there is in there. There you see the cryostat mounted, and there's the mirror. So this is when we were, so how a balloon usually works is, these are basically fabricated and assembled and designed by graduate students. And NASA requires you to demonstrate it with a test flight before you go down for the full Antarctic flight. And so we integrated this for the first time a year and a half ago in Arizona. This is the high bay in the edge of Tucson, where we integrated everything. The camera was too delicate and fragile to fly. Like if anything happened to it, we wouldn't have time to fix it. So we were not going to fly that. Also, it wasn't ready yet. The mirror was also too fragile and delicate to fly. So instead, we filled an oil drum with cement to simulate the mass. And we flew everything else to test. So basically, we're showing NASA that the spacecraft works and we know what we're doing. They also view it as like a team building experience, because going down to Antarctica is very stressful. It's very isolated and a lot of work, low sleep and so forth. So it's kind of like a team building process as well. But here you show the kind of as-built stuff. This is the proxy mass. Gyroscope and inclinometers tell us where we're pointed. Star cameras are where we can tell exactly where we're pointed. We also have elevation axis and encoders there. Reaction wheel is down here. This is the structure that's holding everything together. And this is the pivot where things rotate, and up there will be the balloon. So intentionally missing from this is the mirror and the cryostat. A year ago, we set out to Fort Sumner, New Mexico. I have been a lot of crazy places on this planet to observe and do astronomy. This is the most remote place I've been. The most difficult place to work was Chile, but this was definitely the most remote place. There wasn't even a bar. And this is the road from Albuquerque out to Fort Sumner. Just fun fact, the only claim to fame I think Fort Sumner has is that it's where Billy the Kid was killed. Okay, so this was us. We arrived at the NASA facility in the middle of the desert. This is how we arrived. It was a big empty field. We had everything done in parts. About 30 days later, we had the completed payload. So we had to kind of assemble all of this from scratch. And it's, the first time you do it is very difficult because everything's been designed on computer. We sort of test fit some things, but putting the whole thing together is difficult because some things don't work. You have to get a file or a drill. We don't know exactly the right sequence to assemble things, so we're kind of slow and clumsy. Just for reference, what took a team of kind of 30 days to do a year ago, the second time we did this a month ago, it was 1.5 graduate students in a week and a half. So now we are truly ready to do this in Antarctica, and it'll go much smoother. But it's a testament to the hard work of the team and the good design that they've done. So from when we showed up in Fort Sumner, we basically had to construct and put on the shiny stuff, the mylar of the sun shield for the first time. We integrated kind of all the little electronics that are going on to do flight sensor, and we had to test them and show that we could talk to NASA. And then the final tuning of the control algorithms are just how we're actually going to move, and kind of verifying all of these interfaces, which basically NASA has a bunch of kind of heritage 20 to 30-year-old black boxes. We have to talk to those, and those have to be robust when the thing's flying halfway to space. So this was the final test flight assembly right before we went out this door to be picked up by a crane and launched into space. This was us as we're hanging. This thing's called Big Bill. This is a custom crane that holds the gondola. These cables are going out to the balloon way over there. I'll show you those in a bit. Here's a zoom in, and this is at sunrise, so that's like 5 a.m. Basically, you're waiting for the weather to be good. And so the winds have to be stable and perfect. There has to be good visibility. So after 2 weeks of trying, this was our 9th attempt of waking up at 3 a.m. to get everything ready, talk to NASA, go sit on the runway and wait to see if the weather's going to be good. We were pretty exhausted. We were running out of time in terms of the season because this was the last possible attempt we could have. So it was very stressful. And we finally made it. This was the balloon going up. Here's the little movie of it. So this thing is huge. Like you see, there's a sports stadium out there. It's bigger than that when it's fully inflated. This is the view from the sky. So if we put a little GoPro on here, this is looking down. This is that launch vehicle that was hanging the payload. These are the cables where the balloon was laid out. This is a tanker truck with giant helium tanks that was used to fill the helium. This is the high bay we were working in. This is the old airport and NASA facility. I was standing there. The team was standing over there. I was too stressed. I needed to be alone, and I was standing over here. I've done a lot of cool things in my career, and this was, I think, top 3. And the only thing we did was fly a cement can, but it was very cool to see this thing go up. This is an image looking down somewhere near the New Mexico-Texas border, but this was basically at flight. That's looking up at the balloon through the payload. I took this from the ground with a big telescope. So we were about 36 kilometers, 80 kilometers away, and it was about 36 kilometers in the sky. So there's the little payload right there. So mostly everything worked. We tested our control. We found out the things to fix. We had to rebuild our pivot. We upgraded our star cameras, but now we're really ready to go. The solar panels worked. Our readout worked. Everything went well. The test flight was only 4 hours, so we tried to do as much as we can in that time. But you see its kind of trajectory. We could have gone much longer, but at this point the winds had picked up and it was going to start booking it across Texas. So NASA advised us that we just bring it down. So it was only a 3-hour drive to go pick it up then. So we actually cut the flight a little bit short just so it'd be easier to drive and pick it up. So it lands in the middle of a field. This is one of the most remote locations in the US. That's why they launch these things. It was funny, a few months ago, one of the other test flights landed in a farmer's field, and it was all over the news. And it was like, NASA thing lands in farmer's field. They always land there. It's just some days, it's a slow news day. But we landed upright, which was good and bad. Good in the sense that most of the stuff survived, but we didn't need it to. We were assuming that it was going to mostly get destroyed. Bad in the sense that if you think about like luck and statistics, I'm worried that we used all of our luck on this landing and we might have a bad landing in Antarctica. But yeah, we tested kind of all the critical components for basically the gondola and the spacecraft. And to get this thing, we had to fit all of this onto that truck afterward. So basically we had to come in with saws and chop up everything. So it's really, for me, I've spent most of my career building instruments for the ground, which is very sane. You can put it on the telescope only when you're ready. When it's on the telescope, if something's wrong, you can go fix it. You can take it off, put it back in the lab and fix it and put it back. This, you have to spend so much work making sure that everything works and you're not allowed to touch it, and it's going to go up into space. And then after 5 or 7 years of work on this thing that is now your baby and you've literally bled on it, it's going to fall from the sky and crash into little bits in the ground. And that to me is crazy. So it's very stressful, but kind of rewarding. Okay, so this is the plan for observing. We've actually been adjusting this slightly. Basically, Euclid changed what we think we can do and optimize this. So we were planning on doing the smallest field possible. So we have 2 slits shown here. The detectors are shown in dots. The 2 slits are shown here in the sky. So that's the field of view is basically one long slit, 1 degree long slit that we scan. And then we scan for so long the sky rotates, so we build out this kind of butterfly pattern. This was when we were assuming we could only use the old HST Good South stuff. Now Euclid has like a 10-degree patch here, so we're going to go wider to 1 square degree. So we're going to expand that. So that's much better. And so what fields can we do? So it needs to be in the south, obviously, because we're flying from Antarctica. We need to avoid the sun, so that limits where we can look on the sky. The obvious field is Good South, which now will probably be referred to as Euclid Deep Field Fornax, which is centered on that. Inside this field, basically every galaxy is known within that field. It's been observed with Hubble and Chandra and Herschel and Spitzer and ALMA and JWST and will be already LSST, Meerkat, Euclid, etc. So the nice thing about doing this is every galaxy in our cube we will know. We will know its stellar mass, we will have an indication of its star formation rate, and so when we build our intensity map and our map of basically power fluctuations, we know how to map that to distributions and populations of down to individual galaxies. So that, at some level we kind of know the answer in the back of the book, which I think is really important for a developing technique like LIM. We are conservatively allocating that we can spend 200 hours on this deep field, and then we'll have probably another 100 to 200 hours that we can spend on other fields. So this deep field will be about a square degree on good south. With this, we're going to do the power spectrum and stacking. For this analysis, you really want kind of as small of a field as possible for stacking, just to have sensitivity. At the time we were thinking all the galaxies we could possibly stack on are just in this field. Now it's Euclid. But we have a large field of view. So the kind of, I think, natural field size that we'd want to do is about a square degree. We're also planning on doing pointed observations towards known high redshift strongly lensed galaxies to try to get O1 and O3. That we're still trying to figure out what the best scan strategy is. It could be just doing the smallest map possible, but you see that's very highly inefficient because you're not going to be on source the whole time and you're wasting all of this. So we're going to look into also just scanning in elevation along the source. The problem with that is that you can only do kind of one of the spectral bands at once. You're modulating the atmosphere loading, and so you're adding in a systematic, and you have to have your dead reckoning pointing good to about, to a few arc seconds. So we think we can do that, but we're going to be we're still working on that. What will the final TIM data products look like? This was a simulation of what we think the actual data product would look like. Again, this is either, you can think of it as like a cube, or we call it a cube, but it's more like a pencil beam. So this is our field of view on the sky, again about a square degree, and extending from redshift 0.5 to 1.5. So this is a simulation of what we will see. This is still when we are considering that kind of 0.1, 0.2 square degree patch. So this is a movie stepping through every spectral channel in the map. This is the CIB plus line. So this is the astrophysical sky simulated without noise. This is what you'll see. You see most of it doesn't change because it's dominated by continuum, but sometimes there'll be a C plus line that changes that fluctuation. This is just the C plus, so continuum removed. This is just the line. And here you see as it steps through, you see the lines change. This is what we will see on the total thing we will see on the sky. This is when you add in instrument noise. Sorry, I got that slide wrong. I said that's the CIB plus lines, that's CIB only, this is the lines. And then this is everything on the sky astrophysical will see plus noise. So at some level you see kind of why intensity mapping, we're still really early days of this technique. It's very noisy. One day, 20 years from now, when we have a $10 million far infrared instrument in space, we can make maps like that. That will be great. Right now, this is what we're looking at. So this is going to be a real statistical analysis. But that's what it looks like. This was done by my postdoc, Mathilde Van Cook. In terms of what you're actually going to measure, basically you're measuring the fluctuation power of C+, which is a function of position and redshift. And so you're measuring the average intensity of C+ times the bias and fluctuations. So just breaking this apart a little bit, this is the mean C+ luminosity, which is the integral of the C+ luminosity function, which is uncertain at kind of the order of magnitude level. So this is one of the biggest uncertainties we have in forecasting, is we don't know what that C+ luminosity function is, particularly at high redshift. So that is kind of, I think, the first fundamental thing line intensity mapping and TIM will measure. This shows just kind of, again, this is just showing that simulation of everything, all the galaxies in the simulations, what you could see without noise. That's just showing that in a particular redshift bin. So other things we can get at this, so there's other ways we can get at the luminosity function. We can stack, so in that cube, from previous surveys, we know the positions and properties of most of the galaxies in there. So we can break those up by redshift and position and stellar properties, metallicity, star formation rate, and stack and ask what is the average C+ luminosity of those galaxies. Also on the bright end, we expect to have some blind detections of C+, so we expect to detect somewhere between 0 and 10 individual galaxies in this cube. I mean, it's highly uncertain basically because the luminosity function is uncertain. But measuring that number helps constrain the bright end of the luminosity function. So, and then finally we can cross-correlate, which is a way of kind of teasing out the signal using, again, kind of the answer in the back of the book from the previous galaxy surveys. So we know where the galaxies are, we'll cross-correlate that with our map and tease out the mean intensity signal. So this shows model constraints. So here are models shown with lines and blue and green. You see the models are all over the place. There's a huge uncertainty. So even upper limits from TIM will really help rule out and constrain models of galaxy evolution in the C+ luminosity function. This is the constraints from the auto power spectrum. That will be very noisy. From when we proposed TIM using these more optimistic models and kind of assumptions, in the proposal we expected to have signal noise of like 50 on the auto power spectrum. And then from the time when we're about to fly now, we expect a signal noise of like best case 3. So cross correlation is going to be kind of our workhorse. And here you see we can basically constrain most of the galaxies and models very well. So we're going to rule out, so this is just showing the cross power spectrum and the constraints on models. You see these models are very much all over the place, and that's going to be an important constraint. We will also we expect to see some blind direct detection. So this is just showing that cube and extracting spectra across those cubes. So these are atmospheric lines. Some of these we expect to detect C+, and that's example spectrum with the noise and with everything that's shown there. Again, we don't know how many we're going to detect because the luminosity function is uncertain, but it's probably somewhere between 0 and 10. So a handful. This just shows how we can actually constrain the luminosity function with those individual detections. We can also basically calibrate the C+ to star formation relation through stacking. So again, we know all the sources in that field. We can break them up by redshift, and this shows the signal noise we expect in the redshift range for all these lines. So these lines, they have been observed in the local universe with, for instance, ISO and Herschel. Some of them have been observed in the most massive galaxies, extreme galaxies with ALMA at very high redshift. Over this redshift range, very few have ever been observed. And so this is unique space that ALMA can't reach, and there's no other platform and space in the far infrared. So this is the forecasted signal noise on that line for all the galaxies known of like a year ago. So this will change because we'll have more galaxies with Euclid. So for C+, we'll have signal noise of Bern, about signal noise of 34. So we can break this up by stellar mass and redshift and measure this. We'll also measure OIII and OIII, signal noise of kind of a fewish, but we can break that up into a few bins. So this is, again, unique parameter space that complements direct measurements we can make with ALMA. Finally, we can do pointed observations of mainly, I used to do lens sources. The lensing is nice because it magnifies the sources by about a factor of 10, which saves you about a factor of 100 in observing time. So that means that a line that would be impossible to detect in an individual galaxy is now fairly trivial to observe. So we anticipate we could probably observe about 10 of these galaxies and target. I think the most exciting thing to target was things that ALMA can't do, basically OIII88 and OII63 at kind of redshift 6. So this shows that spectrum again I was showing of M82 and also a simulated one, and this shows the TIM band at various redshifts. So this I think is the sweet spot right there, redshift about 4, where we can get the OIII into and OII lines. And this will take kind of a few hours per source. The other thing that I've been thinking a lot about lately is, this is a whole other talk, but for a South Pole telescope, usually we spend most of our time observing the cosmic microwave background. In the course of doing that, our cameras are now so sensitive that as we observe the sky over and over, we can now see things changing. So we're doing transient astronomy, time domain stuff. It turns out that most of the things we're seeing, well, most of the things are quasars or blazars that are varying, but most of the actual transient events are like M-dwarf stars that have very luminous flares very nearby to us. So most of the transient events we see with SPT have been nearby transient sources of stars, very nearby. And we're looking through the plane of the galaxy, so they're all nearby. So it kind of got me thinking, like, what if we look towards the galaxy, what will we see? And actually, a few of us were talking about this, and we decided to try it with SPT. So for about a month a year, we now use SPT to look at our galaxy. This is an image of our Milky Way in the 3 SPT bands. This is about 2 months over, 1 month over 2 years, so 2 months total. Observing, there's the galactic center, Sag stars. So we have a project looking at the variability of that and the polarization variability. That's, for reference, Sag B2. That's the most intensely star-forming cloud in our galaxy. Lobster Nebula, Cat's Paw Nebula. The thing that was like immediately just kind of changed, I'm used to observing faint things. There's so much signal here. It's really bright. It's really easy. So it got me thinking about TIM. Before we had kind of discounted using TIM because it's relatively low spectral resolution and spatial resolution. But realizing that there's so much signal to hear, and in case something goes wrong, and also in an effort to maximize science and the number of fields we can engage with, we're looking into mapping some fraction of the galactic plane with TIM. So to start, a grad student and I have been thinking about this, and this is a Herschel hi-fi spectrum of Sag B2, so that bright spot right there. This is basically 1 pixel with Herschel hi-fi. This is the spectrum. You see that it's a whole forest of lines, okay? I merely used ChatGPT to take that spectrum, convolve it with the TIM spectral resolution, and then looked at the lines. And so originally when we were thinking about this project, I was assuming we would detect the CO lines and we could look for kind of dense clouds off the plane that had not been observed, and we could measure their temperature with the ratio of the CO lines. That was my initial kind of notion of what we were trying to do. I now realize 2 things. One is that those lines, there's so many absorption features that those lines aren't the obviously most distinctive features in the spectrum we will see. So now I'm kind of back to square one of what we're going to actually see. Probably we'll do something like build a template and fit these to it, but I'm still playing around with what we're going to do with this. Of course, this is the brightest spot in the galaxy, Sag B2. We would do a survey, so this is still unique space. There's never been a wide field spectroscopic survey, blind spectroscopic survey of the galaxy. So yes, it has kind of coarse spectral resolution compared to what people normally do in the galaxy, but it's unique space and a unique far-infrared platform that we don't have. So talk to me if you're interested or if you have some ideas about that. Okay, looking forward with TIM. So why NASA really cares about this? It's not actually the science. Like the balloon program is not to do science, it's to develop technology and the workforce. So in terms of technology, what this is demonstrating is kilopixel low noise kit arrays and a low power RF sock-based readout system. So this is kind of on the technology development path for a probe and for a future far-infrared mission. That's what NASA looks at it. In terms of technology development for science, we will work out the kind of logistics and analysis pipeline needed to do line intensity mapping. We will probably run into difficulties in analysis that we'll have to develop techniques to deal with and overcome. Again, nobody has really done this. Nobody has done this yet with bolometer arrays and grating spectrometers and so forth. So this will also raise the science readiness level of the LIM field. The other thing that the balloon program does for NASA is workforce development. All these grad students have had to work on instrumentation, work at NASA facilities, develop new technologies, these are the people that will go become NASA staff. So NASA really does look at it as this is workforce development. They even look at it as like they're training me to be like a PI or whatever. You know, it's kind of interesting. We're also thinking about cross-correlation. So this is probably, you know, where the first intensity mapping measurements will come from, is cross-correlating. So in the background here is basically a 1.5 hour pointing with the Meerkat UHF band. So the actual image is much bigger than this, it wouldn't fit. And that's just one pointing. We actually have about 50 of these over 100 square degrees of the SPT field. This is 100 microjansky RMS, and remember this, I'm showing you the continuum, but this also is a cube. And so interestingly, this covers H1 from 0.4 to 1.5, so good overlap with SPT. Also, we have a test camera that goes on SPT in the summers. It's called SPT Slim. That's a spectrometer on a chip bolometer array. That operates from 120 to 180 gigahertz. That will measure CO between redshift 0.5 and 2. So we have all of these kind of tracers of C+, CO, and H1 in the same redshift range. So cross-correlating them seems very obvious. I think a problem is going to be, well, first coordinating so that we're all observing the same patch of sky, but then the same mode. So for instance, an interferometer measures different modes on the sky than a bolometer array scanning across it. So that we have people thinking about. It's kind of subtle and kind of complicated, but we hope to make some progress there, and that will be a possibility. So in terms of the schedule, we're about here. We're gonna have our kind of mission readiness review, and then in about 6 months, we're gonna go to Texas to demonstrate the full assembly to NASA that we're ready to go. Then we'll pack it all up into crates, ship it to Antarctica, and we'll do our science flight from McMurdo in Antarctica about exactly a year from now. Then it will hopefully have a soft landing. Things will come back, we'll get the data, we'll start working on maps. In about 2 years, we hope to have first results. Current status, so the flight arrays, the fabrication is in progress. We have finished the test arrays, and basically we're about to just turn the crank on the rest of them at JPL. The gondola rebuild, this was a few weeks ago. The rebuild is completed. It's been souped up, it's great, everything, and it's been integrated with flight software. Cold optics and the sub-Kelvin system is integrated and ready to go. And we're on track to ship to Palestine. So this is kind of status of the team. So future, so, you know, I think two things have been kind of changing rapidly in millimeter astronomy lately on ground-based stuff. One is that CMBS-4 was a thing, then was canceled. And the other is that line intensity mapping was recently endorsed by the High Energy Physics P5 report, which said that this is a promising technique for the future, which basically opens up the spigot of funding and R&D from the Department of Energy. The enabling technology from the ground is going to be on-chip spectrometers working between kind of 100 and 300 gigahertz. There's also work to be done with coherent receivers like CO, but I think this is going to be kind of the workhorse. The platforms will basically be all the current generation of CMB telescopes. So you can imagine just all the old CMB telescopes, you can convert their cameras into imagers and turn that, you know, what used to be broadband imagers into spectrometers. The signal would be kind of CO at cosmic noon and C+ at cosmic dawn. The science would be growth of structure, non-Gaussianity, star formation history, etc. So I think this is going to be promising for the next 10 years as a way to make progress in the field. In 2023, line intensity mapping was endorsed by the US Energy Physics P5 report, basically saying, you know, think about this as a technique for 2035 and beyond. So the idea is the next thing you work on is stage 5 spectroscopic survey. After that, it's line intensity mapping. That was a big green light, though, for a technique. In terms of NASA, you can think of TIM as kind of a pathfinder for a probe that would be $1 billion class, and then a flagship, which would be $10 billion class. In terms of sensitivity, there's a plot by Matt Bradford. This shows Herschel, Pax, and Spire sensitivity. This is TIM, so we're more sensitive than Spire. And this is where basically if you make a cold kind of 2-meter class space telescope, this is the sensitivity you would get. The big gain is here is going cold. This would actually be similar size to TIM, just cold and in space. But you see a huge leap in sensitivity of like 4 orders of magnitude. The next big leap would be a flagship like we considered for Origins, which would be somewhere between like a 5 and a 10 meter, cooled to 4 Kelvin, with something like 100,000 detectors, not 10,000 detectors, and the sensitivity would be shown there. In terms of science, so I think the most important, just fundamental case is linking up our spectroscopic capabilities between the ground with ALMA and JWST from space. We have this huge gap at about 100 microns that we cannot trace these very important lines like Passion Alpha and C+ across the entire history of cosmic time. And I think for truly understanding galaxy evolution, we need to be able to see these galaxies with the same set of tracers all the way across cosmic time. So I think that will be a very important bridge between ALMA and JWST, even if it's 10, 20 years from now. So the future of space line intensity mapping. So first of all, SphereX is launched. That's near infrared. Prima is wrapping up its phase A study with NASA now. We studied a 6-meter far-infrared telescope cooled to 4 Kelvin for the decadal. We thought we could make it for about $5 billion. But by the time it was probably done, that was probably more going to be like a $10 billion thing, a decade from now, once you get all the bells and whistles you want on it. An enabling technology would be the SpaceX Super Heavy rocket, which would have a larger fairing, which means you wouldn't need to have the mirror unfold, which means you would save a lot of engineering cost. And so you could just build a big thing, put it on the spacecraft, launch it up. So I think that is the big technology to watch for the next generation of space telescopes. The science cases would include the first galaxies, biosignatures in exoplanets, atmospheres, spectroscopic surveys, and line intensity for the history of cosmic evolution. What data, this is that same simulation we actually made for TIM, we did for Origins. The cool thing about this is that something like Origins or a far infrared flagship would do for spectroscopy in the far infrared what Sloan did for optical spectroscopy, in terms of it would provide millions of far infrared spectra across cosmic time, reaching much further than Sloan did, across a huge wavelength range. The power spectra would chart the luminosity function and star formation history, and these far infrared tracers would provide tomography of the neutral H2 regions and the AGN all at once. So that I think is real power. So I'm done. I'd like to thank the TIM team, particularly all the grad students and young scientists. I kept the slide. This used to be the people on the job market. They're now fine. My grad student Frank is just defended, and he's going to Princeton as a Dickey Fellow. And Jessica got a faculty job at UChicago, so I don't have to go push around them for job stuff anymore. But it's been a real pleasure working with the team. It's a real cool team to work with. I'm excited to go to Antarctica with them all. So conclusions, we successfully test flew, and we're preparing for a science flight in Antarctica about a year from now. Tim will make the first measurements of the C+ power spectrum, or constrain it, and really constrain the C+ luminosity function, the first direct spectroscopic measurement of the cosmic star formation history. Line intensity mapping in general is recognized as a powerful kind of future probe for galaxy evolution and cosmology. And a huge thing was this endorsement by the P5 report, which means a green light for thinking about this for the future. Thank you. I had, as an aside, this is like when we were coming up for the name, we were writing down all the possible configurations of terahertz and intensity mapping, and we finally came out to TIM, which seemed a little bit contrite, but we were all big Monty Python fans. And so Tim the Enchanter, this was, if you've seen Monty Python, the Holy Grail, that's kind of what we decided our mascot would be, is Tim the Enchanter. So this is a great film. That's kind of the reference that we were making with that name, but yeah.
Is that the guy on the balloon?
That's so we had my old My old college buddy is a designer, so we have him make the SB t-shirts and I had him make this. But yeah, that's Tim the Enchanter on the balloon with the telescope. So that's kind of that'll be the t-shirt for when we deploy.
Questions for Joaquin?
Is it just one long balloon flight, or there will be multiple?
Depends. So from Antarctica, basically you you have McMurdo here, you launch and then it goes around. There's wind circuits that go around, and so you can go around. And this typically, like the average is like 20 days to go around the continent. Sometimes it's 10, sometimes it's 30, but it's typical. But yeah, you're up in the air that whole time in the daytime because it's 6 months of daytime, right? If we wanted to do another flight, then this thing comes down and crashes. We go out and we have to cut it all apart, put it onto a small airplane and bring it back, rebuild it all. Probably everything will be smashed. Like that mirror will probably not be salvageable. It's carbon fiber, it's gonna be cracked. The cryostat, maybe it survives, but it will have to be rebuilt because it'll be dented and smashed. Perhaps the detector arrays will be fine, but by that point we would want to upgrade them most likely. So usually what happens is you do this one flight, you've got one chance at it, then you repropose again, and the balloon funding cycle is in 5-year chunks. So then we would repropose to rebuild it and do it. I think, in terms of what we could do, we've thought a lot about it, this, of what comes after Tim. And we've already kind of pushed against all of our design constraints in a way that it's already borderline unsafe and logistically difficult. Like for instance, this is so large that it's a sail. And so we can only launch when the wind is very low, which means we have fewer launch opportunities, which means we might not have an opportunity to launch. That was a bad design choice. But I mean, we're trying to maximize science and make it as big and sensitive as possible. Other things, we could try to maximize, it would be hard to get more detectors on there. We're already barely fitting everything in, and we have 7,000 detectors. How could we get to a factor of 2 more? Maybe we could get a factor of 2 more, but that's it. In terms of raw sensitivity, we can't make the mirror any bigger. We couldn't even fit out the door of the high bay. We could try to go smaller and cold, but that makes other complications of you have to make a box for it now and use cryogenics. So it's not totally clear what comes next, actually. Originally, I had kind of assumed that the second flight would be longer wavelength. And so if you think about star formation rate versus Z, and you have this, and that's at redshift 2, Tim is here. I'd kind of thought, well, we could go the second flight, we could go to longer wavelength and go out here. So this would be Tim 2. And then eventually work out our way in sensitivity to like Tim 3 out to redshift 6. That has complications, like, first of all, we're already starting where the signal is absolutely brightest. So going to longer wavelength, the signal is getting lower. And then by the time we're out here, maybe we could do that with these spectrometer on a chip bolometers. That's a possibility, but it's not clear. Like it might be easier and better to do that from the ground at that point. But these are all kind of possibilities we thought about for what to do next. And right now we're focused on launching and doing our science.
Any other questions? So,
I had a really kind of dumb question. At page 23, you were showing us the transient emission. And there was a dip in the how much we go past even at the balloon height.
Yeah.
At like
Here?
Yeah, here.
Water.
That is
Water.
water. Just water. Okay. But you're flying at 34 kilometers. Makes sense.
Yeah.
Uh,
how do you control the direction of the telescope?
Two different ways. So elevation is a motor, right? So you have this giant balloon that has a huge inertial mass, like huge. It's basically stationary. Okay, then we have a pivot right there, and then we have a flywheel, a reaction wheel here. And so this we are controlling. This we are controlling the spin of, and we can control the rotation here. So we spin this up to have momentum on our spacecraft, and then we're controlling the left and right motion with this pivot. So it's just a little motor. But this is so big, it's basically like it's our momentum sink, right? That does not move.
So while it's floating, it's very stable.
Yeah, yeah. And massive compared to what we are. I mean, yeah.
Other questions? Okay. If not, so Joaquin will stay until Friday this week, and then tomorrow at 11 a.m. Joaquin will give another talk, seminar talk, same location here on the dusty galaxies observed selected from SPD, and also follow up with all the facilities to all the same dusty galaxies individually. And so I think that's for today. Thanks Joaquin again.